Hi, I'm Brent Mantooth, and today I'm going to be talking about my review of some Astronomik MaxFR narrowband filters for fast optics. I'll be looking at these filters at two configurations with my Edge HD Schmidt-Cassegrain telescope at f7 and at f2.2 using HyperStar. And just as one example of what you can get out of these filters is a recent image I acquired of the Crab Nebula. So as I got into doing this, it turns out there was a lot of depth as I figured out what was actually going on with these filters. As a result, this review is a little bit long. I'm kind of hitting most of the topics I'm going to talk about here in an outline, and I'll have chapter overviews so you can jump between sections if you're interested in any particular topics. So what I'll be looking at today is three wavelengths for hydrogen alpha, oxygen 3, and sulfur 2. I'll be looking at most of these with two bandwidths of 12 nanometer and 6 nanometer bandwidths. Each of these filters is indicated by Astronomik to be rated down to a lowest rated f-stop where they should function well. So this is an example of the hydrogen alpha filter at 6 nanometers. It's a dichroic filter, so it ends up reflecting back any light that is not the particular passband associated with that given wavelength. So we can see here that this filter should be providing about 95% transmittance and work on any f-stop down to about f2.1. As I went through this and started seeing various trends and the characteristics of the halos and the signal comparison, I didn't necessarily understand what I was seeing, and some of the results really surprised me. As I dug deeper into what's going on in these cases, I had to get into kind of the science of how these narrowband filters work. And that's where I really started to learn and understand and appreciate you need to be very careful and selective in your narrowband filters to make sure you understand what's going to work for your particular system. And from that, we can actually drive to some conclusions on, are these filters good? So in this case, I'm going to be comparing the telescope in two different configurations. One using the 0.7 focal reducer, giving me an f-stop of f7, and the HyperStar version 4 giving me an f-stop of 2.2. In both cases, I'm on my 9.25 inch Celestron Edge HD Schmidt-Cassegrain telescope. I was able to acquire these about 10 days apart, but across those 10 days there was some big differences in the moon phase between being essentially a new moon and mostly illuminated. I am in a Bortle 5 to 6 zone, so there's a moderate amount of light pollution. And in both cases, weather's not been great, so my seeing for both of these nights wasn't the greatest. As a quick walkthrough for each scope configuration, this would be the layout for the 0.7 reducer configuration. And if you're interested in the details, you can pause the video. And here I have my HyperStar configuration. Again, everything is documented in detail on the left. A few notes about this configuration. The HyperStar does put the camera on the front side of the telescope, and that means we have cables to run. I have used a cable routing system to give me an arch for the cables that should minimize diffraction spikes coming off of the cables. I've also flocked the inside of this scope. The coating that is used by Celestron for this is kind of a grayish paint that does have some reflection, so I've added some flocking in here to minimize any potential stray light or reflections. In the event that you decide you want to flock your telescope, make absolutely certain that you account for the exact rotational alignment of your corrector plate. That is something that is fine-tuned by Celestron when you get your telescope. I do use a aluminum dew shield, and to help with that cable management, I got some extra grooves so that I could feed the cables through the dew shield. So for each of the images that I analyzed, I collected three 500-second images with the camera at unity gain, and for this camera that's at 100, and I used a pedestal offset of 20. I ran autofocus after each filter change, and then to analyze the images, I used PixInsight and the weighted batch pre-processing script. I applied image calibration with the indicated data here, and image registration with a common reference across all filters to my first hydrogen alpha image. I then integrated each of the three images. I selected no scaling, no normalization, and an averaging calculation. So any images I show, I was going to display using the PixInsight auto stretch function from the screen transfer function. And any of the cross-section analysis I did, I used ImageJ and then plotted it either in Excel or Python. After doing all of this work, I realized that the calibration process may actually be changing the data in ways I was not expecting. So I went back and compared some uncalibrated frames, and for the most part, it seemed like the difference after calibration was mostly just a uniform offset on the results. So I think most of my discussion on the analog to digital unit signal analysis should be okay, but there may be some offsets. So let's start by looking at the images. So any image that I show you that uses the 0.7 reducer is going to be highlighted in red, and all of my HyperStar images are going to be highlighted in blue. We can also see a qualitative significant difference in contrast. The HyperStar has collected a lot more light, so we're seeing a lot more contrast. First off, in looking at the whole image, if you squint really hard, there might be a reflection here, but it's pretty hard to see. If we compare on the top the 6 nanometer to bottom 12 nanometer images, it's really hard to visually see any difference as we look across these, but we'll be going back for a detailed analysis shortly. When we look at the Sulfur 2 images, I only have the 12 nanometer version of this particular filter, and in both cases we can see for the 0.7 reducer there is some form of reflections, and with the HyperStar there's also something going on with the star on attack. When we go to the OIII channel, we can see that there's actually multiple reflections, especially for the 0.7 reducer, and it shows up for both the 6 and 12 nanometer filters. There's also a little bit of structure here in this particular one, which I think is a result of my off-axis guiding prism being ever so slightly in the imaging path that's created this strange pattern. When we look at the HyperStar configuration, we do not see all of these potential reflections that we saw with the reducer. However, there is some structure in here that we'll be looking at in detail. So let's start some of this analysis by looking at halos from on attack. And let's think about what we're actually seeing with this star. And we can do that by looking at its apparent magnitude. That apparent magnitude, m, is the brightness of a star as observed from Earth. So it accounts for the intrinsic luminosity of the star, its distance from Earth, and any extinction caused by the interstellar dust clouds in its line of sight to us. So what I'm going to do is compare what seems to me to be one of the other brightest stars in this image. Compare the apparent magnitude of this star, which was at 7.52, to on attack at M1.77. It's a reverse logarithmic scale. Lower numbers are brighter, and you can calculate the difference in brightness using this equation. When we push that through, we see that this star is 200 times brighter than what seems to be one of the next brightest stars. Even if only 0.01% of the photons reflected inside the optics off of on attack, that's still going to be 200 times the number of reflecting photons compared to all of the other stars. So we're going to be seeing it from this bright star that's many orders of magnitude brighter than most other objects in this image. So let's go do a detailed analysis of what we were seeing for on attack. So I've zoomed in for each of these images using the 6 and 12 nanometer bandwidth filters on the HyperStar, and we can actually see a little bit of a fringe pattern. We're going to go explore that in a couple of images. I'll also say that I had a really good collimation at the start of the night, and when I went to go set up my images, I think that I forgot to tighten one of the rotation screws for the field rotation of the HyperStar. So I think that's what's causing some of the potential coma that we're seeing here as essentially a collimation error. If we compare that to what we saw with the H alpha with the 0.7 reducer, we don't see these diffraction patterns, but if you squint really hard, there is kind of one circle for the 6 nanometer filter, and I don't think I see quite the same thing for the 12 nanometer bandwidth filter for hydrogen alpha with the 0.7 reducer. Now if we go over to the Sulfur 2 image, there certainly seems to be something else going on. With the HyperStar, we do seem to get a ring in addition to this fringing pattern that we see here, similar to what we saw with the hydrogen alpha. And when we go to the 0.7 reducer configuration, there seems to be a very large reflection that I'm guessing is on the order of about 2,000 pixels wide. If I look at this for the oxygen 3 filter, which is typically notorious for reflections, in the HyperStar for both bandwidth of filters, again we see kind of this repeated pattern here. And I think that some of the spikes that we're seeing here is a result of some of the cable routing that we're seeing. Now, when we go look at the same filters, but with the 0.7 reducer, again, we're seeing this rather large reflection that seems to be very different than what we're seeing on the HyperStar. One of the first questions I wanted to consider is how bad are these halos? What is the signal coming from them? So I used a technique that I developed in my last video, which I'll put a link in here if you want to go watch exactly how I did this, but using PixInsight, I would take the two bandwidths and put each filter bandwidth in a given color channel out of a color image. Save that as a 16-bit TIFF, and then go into ImageJ to extract it. And what that does is let us compare the signal for the exact same region out of these two channels. So when we do that for the OIII halo, along the line that I've illustrated here, we can see that visually at this point, there's not that much difference. We have our 12 nanometer signal in the purple and the 6 nanometer bandwidth signal in the blue. If I subtract out the background, that's kind of the common background that's outside of the halo here, so that that goes to 0. And then I use a moving average filter. In this case, it's about a 10-point wide moving average filter. We can see that we zeroed out the background. And if we look in the region of the halo, we can see that the 6 nanometer bandwidth filter provided about 5 analog to digital units, and the 12 nanometer bandwidth filter provided about 10 ADU worth of signal. So it's really not that much signal, kind of within some of the, almost like the standard deviation of this signal magnitude. But you can definitely see it in the image, and it is something you'll have to contend with to have really nice images. So in doing some reading on cloudy nights and watching some other videos, there is a way to understand where these reflections are coming from by doing some simple calculations. If you calculate the diameter of the halo in your image and record that as diameter in pixels and multiply that by the pixel pitch of your sensor, multiply that by 1,000 to convert our microns to millimeters, and you can get the halo diameter on the sensor in millimeter units. You can then take that halo diameter and multiply it by your focal ratio to actually get the total light path distance from sensor to the reflection. So for example, if that reflection happened at your sensor and bounced up to your anti-reflective window and then back down, you would have traversed this 8.75 millimeters twice. Or alternately, if we would have calculated that as being that close to 17 or 18, close to that 18 millimeters, if we would have calculated that total light path distance to be about 18 millimeters, that would have corresponded very closely to the light bouncing off the sensor to our anti-reflective window and back. So often what you can do is divide that total light path distance by 2 and start to estimate kind of where that might be in your imaging train. As I went through this exercise, I started realizing that there's actually a lot of reflective surfaces that are in the sensors. You can see that there is a cover slip, or there is a anti-reflective window that protects the sensor. And then actually on the sensor itself, there is a cover slip in addition to the optics associated with the sensor itself. And you can see at different angles how reflective these may be. I also found it interesting as I compared the product literature on some of the various websites that the product images actually include a mask over the circuit board and window for the sensor that doesn't seem to be included in the product that they sell. So as we look at the details here, there's actually several layers to be concerned with. The sensor itself, there's actually a set of microlenses on top of the sensor that help to collect a broader quantity of light to bring into the sensor, and there's actually a cover slip that sits over that, in addition to potential reflections that could come off of the chip support or any of the contacts around here. So let's go back and look at some of these data. If we look at our Sulfur 2 image, we had about a 2034 pixel wide reflection. So we put it through our calculations, multiply that by our pixel pitch, convert it to millimeters, and we see 7.6 millimeters. This was with the 0.7 reducer, so we multiply that by 7 and get a total of 53.2 millimeters as the total light path distance. So if we just approximate that by dividing by 2, the source is about 26.6 millimeters from the sensor. that might be on the ballpark of reflecting off the sensor to the filter and back. When we go over to the oxygen-3, the reflection was a different size. So in this case, it was about 1,407 pixels. And if you look kind of hard, there's almost like an interior, you can see the secondary mirror reflected here and a second one here that's maybe of a different size. So there might be multiple reflections going on in here. When we take it through the same calculation, we get that the source is about 18.5 millimeters from the sensor, which is going to correspond to some of the reflections that you might see associated with the sensor to the bottom of the anti-reflective window. Most of the reflections that we're seeing from these really big halos seem to be associated more with the sensor as opposed to light bouncing around and off of the MaxFR filters themselves. If we go back and look at the oxygen-3 data, there's actually quite a bit of a pattern associated with the reflections. We have our original circle, and if I advance it here, you can see that there's actually other circles and a rather geometric pattern. And after doing some reading, there's actually a really good thread that I'll include a link to down in the comments on cloudy nights, where they identified that this may actually be associated with reflections and diffraction occurring off of the microlenses that are up there. These are irregular patterns, so when you illuminate them, they can actually cause this diffraction pattern that creates these multiple reflections. And there's actually a technique where you can adjust the tilt of your sensor and tune up your sensor so it's exactly perpendicular to your image axis using a laser and generating these diffraction spots. So this is just an illustration where I've taken my laser using my rig to adjust sensor tilt, and you can actually see a reflection off of the protective window, in addition to the diffraction coming off of the microlens array on the sensors. And here you can kind of see a different angle of that. So what we actually seem to be seeing in this oxygen-3 case, we are seeing a diffraction from Alnitak hit the microsensor array, diffract, reflect back up to our anti-reflective window, and come back down to our sensor that is creating these large spaced reflections. So it's actually more attributed to a characteristic of the camera as opposed to a characteristic of the filter. Now, why does this happen for oxygen-3 and not the other filters? It may have to do with the reflectivity of the optics being more reflective in the shorter wavelength, the 500 nanometers associated with oxygen-3 compared to the 650 nanometers associated with hydrogen alpha. So that explains a potential wavelength, but again, we didn't see these reflections for the HyperStar. So my best guess on that is that as we have magnified the image a little bit more using the 0.7 reducer, that we're actually illuminating enough of the microlenses to really generate this diffraction. When we go to the HyperStar, we're actually focusing Alnitak into a smaller area, so maybe we're not hitting enough of the sensor area to cause the diffraction, but that's only guesses here. So with the concept of microlens diffraction, if we go back to our hydrogen alpha and OIII images with the HyperStar, when you go back and look at the fringes that we see here associated with these two filters, they actually, if you align them so that we see the diffraction pattern here and set them side by side, you can see that they actually have a different frequency with which they're going out. So that tells us that we have a wavelength dependent spacing, which is one of the key things you would expect to see in microlens diffraction. Now, if we go back and look at our sulfur 2 image with the HyperStar, we actually saw kind of a ring that was occurring at about 172 pixels. When we go through the math, we see that the reflection source is about 0.6 millimeters from the sensor. And it turns out, if you go back and look up how many of the Sony sensors are made, you have your microlens array, and they put a protective chip cover slip over the system to protect all the microlenses and sensors. And that cover slip tends to be about 0.6 millimeters away from the microarray. So all of this is kind of lining up that what we're probably seeing in all of these cases is a reflection that's occurring due to the diffraction of the microlenses reflecting on the cover slip, or in the other case, with the 0.7 reducer, we're actually getting a primary reflection off of our anti-reflective window that's causing all of these halos. So it really does seem like the MaxFR is that we're not getting these halos due to an effect of the filter, but rather an effect of microlens diffraction from this particular sensor and camera configuration. Next, we're going to look at the effect of filter bandwidth on nebula signal. We're going to start by looking at the H-alpha emission. We're going to be looking at both the 6 and 12 nanometer bandwidth filters. The whole purpose behind most narrowband filters is to only allow the wavelength that you're interested in to pass and block all other wavelengths as background. So conceptually, the narrower your bandwidth, the less background signal there will be, which should provide better signal to noise and better contrast. Now, where this becomes challenging is that the transmission spectra that we see in documentation like this is typically for a 0-degree incidence angle. When we use things like the HyperStar that give us really low focal ratios, the angle of incidence is much larger in those cases, and the transmission characteristics of these types of filters change as a function of the incidence angle. So if the filter is not designed to pass light for these higher incidence angles, you end up reflecting all of that H-alpha light out, which has the same effect of shooting with a higher focal ratio scope. So as we started in the images, to just look at the images, it was kind of hard to tell exactly what some of the differences were between the 12 nanometer and 6 nanometer bandwidth filters. So here I've looked at a HyperStar image. I've done a cross-section of this image. We can see the results here with the 12 nanometer in purple and the blue line representing the 6 nanometer. The dark region here corresponds to this part of our cross-section. If we define this as background and subtract out that signal, we get the trace that we see on the bottom. So essentially, the difference between background and the top peak of our signal is going to be contrast. The higher this is, the bigger the difference between a bright region and a dark region. This really surprised me at first. We observed better contrast with the 12 nanometer bandwidth filter compared to the 6 nanometer bandwidth filter in our HyperStar. This really surprised me, and I didn't understand the results, especially when we go over and compare what we saw in the F7 configuration. For the 12 nanometer and 6 nanometer bandwidths, we can see that we had a similar signal difference. The 6 nanometer had less signal. We're again looking at this dark region here. So I would have actually expected this less signal because it means that there is less background. So it's doing a better job filtering. So if I now subtract the background out of these two signals and we compare them, we see that when we look at the bright region of the Flame Nebula over here, I'm probably looking at this side here that corresponds with this peak, we get the exact same signal. There is no contrast enhancement. One of the other things I want to point out about this is somewhat the advantage of HyperStar. In both cases, we're looking at 500-second exposures. And in 500 seconds at f7, I'm only seeing about 200 units of exposure. When we compare this to HyperStar, we're getting signal on the order of 2,000 to 2,500. So this is one of the benefits of imaging with fast optics, is that you accumulate signal much faster. And if you compare the apparent noise of this data with the apparent noise that we see at f7, we can see, again, more advantages to collecting light that fast. Now, if I were to go to a different part of the image and do the same comparison, this time with the Horsehead Nebula, looking at a bright region of H-alpha, dark spot of the Horsehead, and back to bright region of the hydrogen alpha, we can go through the same process. 12 nanometer signal is greater than the 6 nanometer, subtract out the background. And again, our 12 nanometer data was greater than the 6 nanometer with the HyperStar, but we saw these same signal intensities out of the 0.7 reducer. This was really confusing. Why do we get the same contrast at f7, but that we actually get better contrast with the 12 nanometer filter? I really was expecting the opposite result, to where the 6 nanometer filter should be giving me the better contrast or the higher signal compared to the background. So as kind of a review here, what can we say about these filters? Well, at f7, the hydrogen alpha signal and its contrast is the same for 6 and 12 nanometer bandwidth filters. The transmission of these filters seems similar. There's no difference in contrast. But when we move to the HyperStar at f2.2, the 6 nanometer filter provides less signal compared to the 12 nanometer filter, which is the opposite of what we expected. It seems that potentially the blue shift or transmission for narrow bandwidth for fast optics is not as expected. If we were to compare the magnitude that we saw for the 6 nanometer compared to the 12 nanometer and divide those signals and look across those cross sections, we would see that there's a mean of about 0.79. So the 6 nanometer signal is about 80% that of the 12 nanometer. If we were to do the same analysis with the Horsehead, we end up with about a mean of 75. If I were to do the same analysis with the 0.7 reducer configuration, we're seeing a mean of about 0.9 to 0.97. So essentially, we see the same thing out of 7 configuration, but we're seeing a reduction in signal for the narrower bandwidth filter of about a 25% suppression when we thought we would be getting better signal. So next, let's look at the OIII filter. However, now we actually have 2 emission lines associated with the oxygen 3 emission. The 6 nanometer filter is centered on the first emission line, and the 12 nanometer filter incorporates both of them. I was thinking that what may happen is you actually get a signal boost because you're collecting both oxygen signals at the same time, whereas the 6 nanometer filter, you're only collecting the one primary emission line, and this secondary line is about 30% of the intensity of the primary line at 500 nanometers. So one of my questions was, is the 6 nanometer filter background suppression going to provide better contrast than incorporating both of these wavelengths? So one of the next things I was interested in investigating was the OIII moon gradient. How well do these filters suppress moon glow? Well, on the night with HyperStar, the moon was about 87% illuminated. Here's what we could see that we were imaging with HyperStar, and we can see that the moon was in the ballpark of about 20 degrees away. That produced a bit of moon glow that is the gradient that we see here. So again, using my cross-section technique, I put the 12 nanometer and 6 nanometer filter data in a RGB image, extracted the cross-section, and we have our results here. So again, I subtracted the background, looking at these initial values where it is dark, and then I did a linear regression to describe the moon glow. And we can see that the slope for the 12 nanometer was about 0.2, and that the slope for the 6 nanometer bandwidth filter was about 0.1, so it was about half the slope in terms of moon glow. I'm not sure that it was better rejection of moon glow due to what we were seeing with the Nebula signal. Maybe we're actually seeing a different type of suppression with the lower bandwidth filters. So to really analyze the OIII signal, I had to move to a different target. So we went over to the Rosette Nebula and acquired images using the 12 nanometer and 6 nanometer bandwidth filters. Using the same techniques again, I've shown both of the signal of the cross section that I've shown here, identified a region of background, subtracted that out, and since this was such a large region of background, I've kind of isolated right in here where we're looking at Nebula signal. So when we look at background, we can see that the 6 and 12 nanometer filters have similar backgrounds, and as we go across, often we may have somewhat similar intensity, but there are again cases to where the 6 nanometer actually has less signal than the 12 nanometer bandwidth. The noise seems to be about the same, so it's not as though we're getting better contrast or better signal to noise. If I were to take a ratio of these two signals, we would see that that ratio is about 0.75, which it turns out is really close to the same reduction in signal that we were seeing with HA between the 6 and 12 nanometer. One other analysis that I did considered how filter bandwidth influenced star size. I covered this quite a bit in my previous video, so just to summarize, I looked across 3 stars, subtracted out the background, and can generally say that the 6 nanometer filter reduced star intensity by about a factor of 1/2. So if you're trying to do narrowband targets like Nebula, one advantage of the 6 nanometer filter is that it will suppress the stars which will make image processing a little bit easier because it will already be reducing those stars for you. If you want more information about this, I'll leave a link. So from the data I've shown so far, what can we say about bandwidth and the MaxFR filters? In regard to halo, the halos that were observed depend a lot on scope configuration. The HyperStar had much fewer halos than the F7 configuration, but in most cases I was able to indicate that those halos were more attributable to the camera as opposed to the filter. In terms of star reduction, the 6 nanometer filter seems to reduce relative star intensity by a factor of about 2. That should help make your nebula processing a little bit easier. In terms of contrast, for 3 500-second exposures, at f7, I did not see any contrast improvement or better background suppression between the two filters. At f2.2, the 6 nanometer filter seemed to stop down the HyperStar, providing about 25% less signal than the 12 nanometer filter did. So does that mean that the filter does not actually enable the advertised f2.1 that we were seeing? Contrary to what was expected, the lower bandwidth filters did not provide better contrast, signal, or background suppression for either f7 or f2.2 imaging with this SCT and camera setup. So being a little bit confused with the results and trying to understand why we were seeing a signal reduction for the 6 nanometer filters, I started kind of digging into what's really going on. So why are fast optics and narrowband imaging a challenge? First off, what we're doing, especially as we go to a HyperStar, is we're going to a low focal ratio. Is the ratio of the focal length of your system divided by the aperture. It turns out within this relationship, there is a defined angle associated with the possible image cone associated with the photons coming from various regions of this optical train, and we can define theta using these equations. So if you go through the various f-stops, you can see that there is essentially a maximum angle that some photons will be coming into the system. So as we go from the native f10, which is a very slow collection of light, to very fast optics that would be upwards of f1.8, we can see that that incidence angle is going to become larger. So when we look at that in terms of these filters, the filters that are used are a dichroic filter, and the transmittance of that filter is a function of theta, or of that incidence angle. So why is that? Well, these are dichroic interference filters. They are designed to allow the transmission of a specific wavelength. To do that, they are made of alternating dielectric and metal materials that have thicknesses that are tuned typically between the target wavelength divided by 2 and 4 that facilitates constructive and destructive interference within these layers. The number of layers and their spacing determines the transmission bandwidth and wavelength. These layers and cavity sizes are tuned for constructive interference, which is going to allow the transmission, and destructive interference, which is going to result in reflection back out. As our light comes in at a different angle, that changes the apparent thickness of this filter that has been tuned to enable specific wavelength transmission based on these interference. So the interference is changed as a result of the incidence angle. For example, when we're looking at f2.2 imaging, that theta is at about 12.8 degrees, which results in a thickness that is about 1.025 times thicker for each layer. The result in this is what is known as a blue shift in the transmission wavelength. You can approximate that transmission shift using this equation. So it's a function of the incidence angle and the effective index of refraction. Now, I couldn't find an index of refraction for these filters, and with a little bit of guess and check work, an estimated index of refraction of 2.2 is in the ballpark of where these filters are. So my numbers won't be exactly accurate, but approximate. What happens is as light comes into the system, as we go to steeper angles, these peaks are going to shift to the left according to that angle. And here I'm showing what the shift would look like relative to our hydrogen alpha emission here in this orange-yellow color. We can see that for that 6 nanometer filter, we're actually only going to be transmitting about 50% of the signal due to the blue shift, at least for the light that's coming in at that steep angle. This is one of the reasons for the given filters was slightly redshifted. Count for the fact that as the angle increased, the actual wavelength is going to shift down to center up that emission peak. In reading through several articles on cloudy nights, I came across a few great threads talking about the angle of incidence as a function of f-stop, and actually found someone that had developed some simulations and calculations in Python that look at these particular calculations. So I found a particular GitHub site where their Python code was listed and editable. So I was able to take this code, run it on my own local copy of Jupyter, and be able to modify the code for some of my interests to address specific questions. Most specifically, I modified it to include the particular optics that we were using, and modified the outputs to look at the average transmission that we would see across our given chips. So in this case, that would be to say for the HyperStar with the 6 nanometer filter, it actually predicts that we would only be seeing on average about 86% transmittance. In comparison, if we were to go over to the Edge 11 with HyperStar, it would only be seeing about 72% average total transmittance. All of these calculations are for a APS-C format sensor. If you were to go to a larger scale 35 millimeter sensor, you would actually start to see some fall off around the edges. But I did not run those simulations. But if you want to follow the link that I'll put below, you can download the code and run those conditions yourself. So what we're looking at here is a histogram for the angle of incidence for the photons that are actually going to be hitting our sensor. So in the case of HyperStar at f2.2, some of those photons are going to be coming in at upwards of about a 13-degree incidence angle. Other photons, depending on where they're reflecting on from that primary mirror, may be as low as about 4.5 degrees. So we have this image cone with the central obstruction removed. If we account for this angle with the blue shift, and look at the resulting transmission that will happen as a function of that incidence angle. When we look at the 6 nanometer bandwidth filter, as soon as we hit about f7 with incidence angles of about 4 degrees, we are starting to shift off of that initial peak and decrease the transmission as the peak shifts more and more blue away from the hydrogen alpha, to the point that when we're at our far extreme, we have much less transmission for some of the light that's coming in from the extremities of the mirror. Again, this is assuming that effective index of refraction of 2.2, so the light fall off may be better than this or it may be worse than this. This is just kind of an illustrative example. In contrast, when we look at the 12 nanometer bandwidth filter, we're not starting to shift that transmission line off of our hydrogen alpha emission until we start hitting about this 9-degree level, at which point we're going to be shifting it off. Using this script, one of the outputs is actually a overall transmission that occurs as well, and you can kind of see how that spatially varies across the sensor if your sensor is large enough. In my case, I was using an APS-C sensor, so I don't have some of that fall off near the edges of the sensor. From that particular analysis, I was able to get an average transmission that would be expected from these filters. So for the F7 and F10 configurations, whether we were in the 6 or 12 nanometer bandwidth filters for all the cases that I tested, we can see that the anticipated transmission was 99%, which is pretty close to what I feel that I was getting. We saw the same signal from all of these filters for the F7 case that was tested. When I went to the HyperStar configuration, the 12 nanometer filter was giving us more signal than the 6 nanometer. This is estimating an average 86% transmittance that corresponds pretty closely to that 75 to 80% that we were seeing in some of the previous images. We see similar effects for the OIII as a function of bandwidth. So essentially what's happening, the filter is having the effect of stopping down our telescope or our optics and not allowing these high incidence angles associated with the fast optics actually pass through. So we're actually decreasing or filtering out some of the light that we're actually interested in. In the case of the Edge 11, it's actually got an even lower f-stop so that you're actually sampling angles out here on the order of 15 degrees. So if we were to put them through the same calculation, you would see that the 6 nanometer filters are actually only allowing about a total of 72% transmittance. What does that say about our 6 nanometer filters? Based on the data that I have, you're not getting any better contrast by eliminating more background, and you're having the effect of stopping down your scope with less transmittance. So at least for my case in HyperStar, it really seems like using those 12 nanometer filters is by far going to get you the best signal possible, and they're much less expensive. So for most HyperStar imagers, I'm going to say go with the 12 nanometer filters. Maybe there's other conditions where the 6 nanometer will show benefit, but not from the data I have seen here. As I was reading more, I was also seeing that the microlensing that we've seen can not only cause some of the diffraction and reflection issues, but that these microlenses have a certain acceptance angle, such that as you go to really fast optics, these lenses may not be able to collect some of that light. I was able to find a few examples with some older Kodak CCD cases to where in the case of about 15-degree angle of incidence, much like we were seeing with the 11-inch HyperStar configuration, you could be losing upwards of half of your signal, at least from the horizontal component of these microlenses. In the case of this CCD, the horizontal and vertical microlenses are not in the same proportions, so they have different characteristics. And looking at one of the KAF series sensors, they did publish their angular dependence, and at least going out to about f.1.8, it didn't really matter. So how much should you worry about angular dependence of the microlenses on your sensor? I would say probably don't worry too much, because most photographic cameras can often use lenses down to f1.8. So I would assume that many of these microlenses are going to enable f-stops down to about this level. However, that's an assumption, and I could not find the equivalent graph for the Sony IMX chip that is used in my sensor. So what do I take away from all of this as a fast optics summary? Fast optics are great for rapid signal collection. However, really taking advantage of this light collection requires attention to detail to collect what the optics are actually providing. Misapplication of some concepts may defeat your fast optics, such as selecting too narrow of a bandwidth of a filter. So make sure you understand all the bottlenecks in your system to decide how you really want to optimize it. And you may need to consider sensor acceptance angles, filter bandwidth, and filter tuning and pre-shift to make sure that it's going to work for the potential range of focal ratios that you may be using these filters for. Thanks for listening. I may try this on a few other scopes and see if I get similar response. Please leave comments, questions, or ideas to try, and clear skies and good imaging for you. Thanks.